Recording started.
Hi everyone. It looks like we don't have anyone coming to this session, and I know that we switched the session from Thursday to Friday because of having a technical problem on the whole area in the north. So anyways, I thought what I'd do is record this, and then what I'll do is I'll send it out to you, and you can use this to study for your test next Thursday. So let's have a look at the first question. Get my little pointer here. So the first question says, be able to identify substances that are an areneous acid or areneous base. So basically, the definition you can see here, it says an areneous acid is a compound that when dissolved in water produces a hydrogen ion or hydronium ion. Remember again that when we get into more advanced chemistry, we're actually talking about this here, H3O+, is what is produced when we have an acid rather than H+. Sometimes we might use the two interchangeably, and we might talk about one and it really means the other. But in actuality, if you saw what was being produced by an acid, it's going to be this ionic species right here. Okay, so what this actually means then is when you're talking about an areneous acid as compared to another kind of acid, and there's different ways of defining acids. There are also Lewis acids, there are Bronsted-Lowry acids. But when you're talking about an areneous acid, you're usually looking at an acid that has hydrogen within the formula itself. So if this question here is saying which of the following substances is an areneous acid, we would look at each of these and we would say, well, the first one here, it's just got carbon and hydrogen. It doesn't look like an acid. It's just a carbon compound, a hydrocarbon compound. This one here is ammonia. This is actually a base. And so this here would actually be the acid, and it could donate this H+ or H3O+ in water. Okay, so that's going to be the answer to this one. Let's go on to the next one. Okay, the next question is similar, and it deals with an areneous base as compared to an acid. And so the definition for an areneous base is a compound that, when dissolved in water, produces a hydroxide ion. And an example here is KOH, and you can see that hydroxide, or OH, is actually in the formula. Excuse me. So again, similar type of definition here. With an areneous base, you're looking at a compound that actually has OH in the formula. Whereas again, if you're looking at something like a Bronsted-Lowry base, you've got a different sort of definition. So again, when we look at these different options here of which one is an areneous base, we notice that ammonia here is a base, but it's not an areneous base. Okay, so the one that's going to be an areneous base is going to be the one with OH in it, and that's going to be calcium hydroxide. All right, so moving right along to screen 3. Now this question here says, identify the solution with the highest pOH. Okay, so again, normally we're kind of more used to dealing with pH than pOH, but we have that formula that allows us to convert from one to the other. So if you look at it here, it says pH plus pOH equals 14. So if you just think about what this actually means, the solution with the highest pOH, well, if you had a really high pOH of, say, 12, and you put it into the formula, then you would see that you had a pOH of 12 here, and the pH would have to be 2. So a high pOH means a low pH. So what we're really looking for here is a solution that has a low pH. In other words, it's really acidic. So let's look at our different options. Well, we look at the first one. Is this going to have a low pH? No, it's a base. It's going to have a high pH. And likewise, this one here is not going to have a really low pH, nor is table salt, NaCl. The one with a really low pH is going to be HCl, hydrochloric acid. Okay, so that's going to be a strong acid. The answer is going to be D. So again, high pOH, low pH, very acidic. Okay, moving along here. So the next question here says, calculate the pOH of a 0.075 mole per liter strontium hydroxide solution. Okay, so I changed the question slightly and make it 0.095 moles per liter. And so how are we going to do this? Okay, so we need to find the pOH. How do we find the pOH of any solution? Well, we use the formula for finding pOH, which is pOH equals minus the log of the hydroxide ion concentration. So we need to find this in order to use this formula. How do we find the concentration of hydroxide? Well, we know we're going to have to use some sort of calculation for that. So step number 2, calculate the concentration of hydroxide. Remember, these square brackets stand for concentration. So we're going to look for the concentration of the hydroxide ion. Now, one thing that's really important to note before we even go on any further is in this formula for strontium hydroxide, we have 2 OHs. That's what the 2 means. So 1 mole of strontium hydroxide is going to produce 2 moles of hydroxide. And that's going to come into play later on. All right, so let's go back to where we were before. We need to use this formula to find the pOH, and we need the concentration of OH. So what we do then is to find the concentration of OH, we're going to go to the next screen, or actually it's below here. Okay, so what are we going to do then? Well, we look at the fact that 1 mole of strontium hydroxide produces 2 moles of OH. We already know that. Okay. Now we know that we have 0.075 moles per liter of strontium hydroxide. But we don't need the concentration of strontium hydroxide. We need the concentration of OH. So we can use it in that other formula. So since every mole of strontium hydroxide produces 2 moles of OH, when we have 0.075 moles per liter of strontium hydroxide, that's going to produce twice as many moles per liter of OH. In other words, it's going to be 0.15 moles per liter of OH. Okay, so now we've got our concentration of OH, and we said that as soon as we found that, we can plug it into this formula to find pOH. So that's what we're going to do now. So on to screen 5. Okay, so using pOH is equal to minus the log of OH negative to find pOH. Okay, so we use the formula and we plug in that formula, the amount we just found for OH, which is 0.15. We plug it into this formula, and so on our calculator we're going to put in 0.15, we're going to press log, and we're going to press the plus minus button to make it negative, and when we do that we get the pOH is equal to 0.82. So that's what we're after. Okay. And there's nobody here to stop me if they don't understand it. Okay. But if you do have a question, please give me a shout if you do find something that you're not sure about here. Okay. So the next question here says equal volumes of 2 solutions, both of pH equals 3.0, are mixed. What is the molar concentration of hydronium ions in the resulting solution? Okay, so we're going to take 2 solutions, they both have a pH of this, we're going to mix them together, and we say what's the new molar concentration of hydronium ions?
You have new mail.
Okay, so let's see how we're going to do this here. Just a sec, I'm just going to check my mail. Sorry guys, I'm just going to have to leave a little bit of blank space here. I have to get back to this email. Okay, sorry guys for the blank space there. I just really had to get back to that email. Okay, so let's see what we're doing here. We've got 2 concentrations. So let's look at the steps we have in the solution. The first step, use the fact that pH equals 2.50 to find out what the concentration of H plus is. Now I could have said the concentration of the hydronium ion for each of the 2 solutions, but I just said H plus. We know what we mean though. Okay, once we find the concentration of H+, then we need to find out what the concentration of H+ is going to be for the mixed solution. How's it going to change it when we add the two solutions together? So, let's see what we do here. So we said we're going to find the concentration of H+ for each of the solutions, and they're identical solutions. Okay, so what we do then, we use this formula. The concentration of H+, or hydronium ion, equals 10 to the minus pH. We can use that to find the concentration of H+, because we're told what the pH is. It's minus 2.5. So we take 10 to the minus 2.5, and we get a concentration of H+. It's going to be 0.0032 moles per liter. Okay, so now we know the concentration of H+, and where is that going to get us? Well, we're going to have a look at a picture to get a better idea of what's going on. So we'll go on to screen 7. And here's what we've got here. Okay, we just found out that the concentration of H+ is this much, 0.0032 moles per liter. Okay, let me just have a look here. Okay, yeah, we found out it was that much. Okay, so concentration of H+ is 0.003 moles per liter for each of the solutions. We need to find out what the concentration of H+ is in the mixed solution. But the thing is, guys, when you've got a solution with a certain amount of concentration, as long as you mix that with another solution, it's just like more of the same solution, isn't it? You're not changing the concentration if you add a solution that has the same concentration as the original solution. So while you're going to change the volume of the solution, you're going to have double the volume, you're not going to change the concentration at all. So the concentration of the mixed solution is still going to be 0.0032 moles per liter. Okay? I hope that makes sense.
You have new mail.
Okay, so, I'm sorry guys, I think my son's coming to the door, I got to open it up, and I'll be right back. Okay, wasn't my son after all, it was my wife with some groceries. So, anyways, we'll go on to the next one. Okay, so what are we doing here? This question says, we'll go on to this one here. Same question, different numbers. It says, prepare 1.75 liters of a solution of pH equals 9.6. What mass of calcium hydroxide is required? Okay, so we're looking for the mass of calcium hydroxide. How are we going to do that? Well, okay, so we're given a pH of 9.6, and we know that we have a base, which is calcium hydroxide. Now, whenever you have a question that has both pH and OH, which is kind of, POH is implied by this here, that you might be dealing with POH, we know we have to go from one to the other. But the question is, do we go to having both in units of pH or both in units of POH? Well, we want to go with both having units of POH, and the reason is that we're looking for the mass of calcium hydroxide, which has OH in it. So it makes sense to switch this pH of 9.6 into a POH. Okay, so if we change the pH of 9.6 into POH, everything will be in OH. And then the second step is going to be, we're going to have to find the concentration of OH. Now, why do we want to find the concentration of OH? Well, ultimately, in this question, we're after the mass of calcium hydroxide. So we're after the mass of OH, and so what we do is we want to find, we know that moles and mass often relate to each other, right? And so, and moles and concentration relate to each other. So once we find the concentration of OH, then we can find the number of moles of OH, and once we find the moles of OH, we can find the mass of OH. And then we can find the mass of calcium hydroxide, because it's related to the moles of OH. Okay, so, again, we wanted to change the pH of 9.6 into POH, so everything is in OH. And so the way we do that is using this formula here again. Okay, so we set it up and we have POH equals 14 minus the pH. So it's going to be 14 minus 9.6, and it's going to be 4.4. So we have a POH of 4.4. And we'll see where that gets us. Okay, good stuff. So, screen number 9. All right, so we found this so far. We're going to go on to step 2. We need to find the concentration of OH.
You have new nail.
And we know that that's going to eventually get us the mass of OH. So, we know that the concentration of OH appears in both these two formulas. But the question is, which one are we going to use? Well, we want to use this one here, OH equals 10 to the minus POH. Why do we want to do that? Because we just found out what POH was. And so now that we know what it is, we can use it to calculate the concentration of OH. So we take that 4.4 that we just found for POH, we plug it in, so it's going to be 10 to the minus 4.4, and we get a concentration of OH of this much, which in scientific notation is 4 times 10 to the minus 5 moles per liter. Okay, so again, we found the concentration of OH. We're going to use that to find moles of OH and then mass of OH. So, on to screen 10. Okay, so let's go to the point where we just left off. We found the concentration of OH is this much, and we're going to use that to find the mass, using the mass of calcium hydroxide. Okay, so how do we go from this concentration that we found of moles per liter of OH to the number of moles of OH? Well, we're going to use this formula here because it relates concentration and N, which is number of moles. So if we want to find N, the number of moles, we switch this formula around, and then it becomes in the form N equals C times V. So then we take the C, which is the concentration we found, and we multiply it by the volume that's in the question, which is 1.75. When we do that, we get 0.0007 moles of OH. So now we have moles of OH, and we can find the mass of OH. And the way we do that is, again, at this point we're dealing with moles of OH. But we somehow have to get moles of CaOH too, because that's what the question is actually looking for. It's not, the question is not asking us about OH, it's asking us about what's the mass of calcium hydroxide. So somehow we have to relate moles of OH to moles of calcium hydroxide. Well, the way we do it again is we say 1 mole of calcium hydroxide produces 2 moles of OH. And now we just found out that we know this many moles of OH, so now we put X for the number of moles of calcium hydroxide to find that out. That's what we want to find out, the number of moles of calcium hydroxide. So we would set up a ratio. I'm not showing it actually here, because in this situation it's actually a really easy ratio. You could do 1 over X equals 2 over this much. But if you just kind of think about the fact that you're going to be having half as many moles of calcium hydroxide are producing twice as many moles of OH, you don't even really have to do a ratio proportion, but you could. Okay, so we're going to get this many moles of calcium hydroxide, which is half as many moles as we had of OH. So now we know the moles of calcium hydroxide. We can use the formula, the periodic table, and the formula for calcium hydroxide to find out the mass of calcium hydroxide. So let's go to the next page. Okay, and that's what we're going to do here. Find the mass of this many moles that we just found of calcium hydroxide. Okay, what's 1 mole of calcium hydroxide? Well, we add up this for calcium, and there's 2 OHs, so this represents the O and the H. We multiply it by 2, and we get, for that whole amount, we get 74.1 grams. Okay, so what we do then is we multiply this decimal. We know we have this many moles. We multiply that by the 74.1 grams, and we're going to end up with this many grams of calcium hydroxide. So that, my friends, is the amount of calcium hydroxide that we need. Okay, so again, always make sure to look over these and to try them over and over again so that you can get them. And if you don't get them, look back at the whiteboarding solution and keep trying until you can get them. So, next question here says, and I think this might be our last one, or second last one. This is our, well, we're getting there anyway. Okay, so this one says, how would you describe the pH of each of the following? So we've got ocean water, vinegar, ammonia, and blood. All right, well, ocean water, it turns out, is slightly basic. Okay? Its pH is somewhere around 7.5. Okay? Just a little bit basic. Now vinegar, we know it's going to be acidic, right? Well, it turns out it's about 3. Somewhere around 2 to 3. Now that's of course not as strong as a really, really strong acid, but it's strong enough. And yeah, we know vinegar is not the strongest acid. Now ammonia, we know that's going to be a really strong base. And I mean, of course it depends on what the moles per liter is, but we know it's going to be somewhere around 12 or even higher maybe. Blood is quite similar to ocean water. It's going to be around 7.5, maybe 7.4, somewhere around there. Okay, so we have 2 slightly basic, and that's going to be ocean water and blood. We have vinegar, which is definitely getting down there as far as acids, but it's not as strong as some. And then ammonia is a strong base. All right. Next question, s'il vous plaît. All right, the next question says we've got 30 mils of 1 mole per liter NaOH. It's diluted by adding this much water, 120 mils. And the question says, by how many units will the pH change? So how are we going to do that? Well, we know if we have a change, we're always dealing with one thing minus another thing, right? Because, you know, if you're looking at a change of temperature, it's going to be, you know, final temperature minus initial temperature. So what we do then is we find the current pH of the solution, we find the new pH after the solution is diluted, and then we subtract one from the other to find out how much the pH has changed by. So what's the current pH? Well, if we look at what we're given in the solution, we see that we have OH, which can give us POH. So if we can get POH from that, then we can get pH from the POH. Okay, so let's get POH. Well, how do we find POH? We use the formula for finding POH, which is POH is equal to minus the log of the hydroxide ion concentration. So, what is the hydroxide ion concentration? Well, we're told that the concentration of NaOH, in this question it says that it's 1 mole per liter. And since 1 mole of NaOH has 1 mole of OH in it, this is also going to be the concentration of OH for the solution. Okay, so we're going to plug in 1 mole per liter. So POH equals minus the log of 1, and that's going to actually equal 0 when you do it. Okay, the log of 1 equals 0. Okay, so the POH of the initial solution is going to be 0. But what's the pH? Well, using this formula, we're going to find that the pH is 14. Man, that's a really, really strong base. Okay, well, we know that sodium hydroxide is a strong base, right? So, okay, so we got a strong base, and it's got a pH of 14. And how much is that going to change? Well, we'll see. So we've got to somehow look at the question. We've got to look at the fact that we've got this many mils, and we're going to dilute it. And how is that going to change the pH? Well, somehow it's going to change the concentration of OH. And we're going to find the new POH, which is going to help us find the new pH. So, let us see how we do this. The mystery is afoot. Okay, so first part was find the current pH. That was pH equals 0. Second part, find the new pH. So how are we going to do that? Well, what are we doing exactly? We're taking 30 mils, 1 mole per liter NaOH, and we're diluting it. So let's see how we do that. What we need to do is, we need to find out how many moles we had in that 30 mils. And once we find out how many moles are in that 30 mils, we can find out how many moles we're putting into the new solution, which is going to be 30 mils plus 150 mils. So we're going to have so many moles that we're going to find out how many they are, and we're going to find out what the new volume is, and then we're just going to use the fact that concentration equals number of moles over volume to find our new concentration. Okay, so we need to find out how many moles we were taking out when we took 30 mils of a 1 mole per liter sodium hydroxide. So we take the fact that number of moles equals concentration times volume, and we've got this concentration of NaOH, and we're taking 30 mils, which is 0.03 liters. We need to change it into liters because we've got liters here, liters there. When we do that, we find out that we have this many moles, 0.03 of NaOH. Okay, so we know how many moles of NaOH are in this 30 mils. And then we've got to take this many moles and divide it by the new volume, the volume which is found by our 30 mils added to our 120 mils. Okay, so when we add 30 mils to 120, we get 150 mils, which is 0.15 liters. Okay, so this many moles, 0.03, divided by 0.15 liters, is going to give us a concentration of 0.2 moles per liter of OH. Well, what can we do when we know a concentration of OH? Well, it fits into this formula, and so we can find a new POH. And again, once we find our new POH, we can find our new pH. Okay, so we do that, we find our new POH, and it's going to be 0.7. So, using the formula that says the pH plus POH is 14, we're going to take 14 minus 0.7, and we're going to get a new pH of 13.3. Okay, so on to the next page. So what we do now is we compare our original pH to our new pH, and we see that it dropped, and it dropped by 0.7 units. So the answer to our question, which was how much is the pH going to change by, is 0.7 units. Alright, so I will be sending you guys out this recording, and again, just want to emphasize the need to work on the review sheet, make sure you know how to do all those questions, all the questions on this whiteboard session, and if you do that, that'll be a good start to the test, which is going to be next Thursday. However, it's also really, really important to do all those assignments as well, which are numbers 8 through 12. So I will let you guys go. Hope you have an awesome weekend, and I don't know if you guys are having snow like we have here in Edmonton, but if you do have snow like we do, enjoy the snow. Take care and God bless.